All right, let's go ahead and take a look at some of the information necessary to complete a selection of questions from the Test 5 material. Okay, so for this one, tiny omission from this question, but it should say here after 1 second. What this is building up to is trying to find a relativistic factor. And so, if we compare against 1 second, it's a little bit easier to see what that's doing. Okay, so for a person inside of a moving object, sometimes this is called the proper time. So you'll see it as sometimes T0. Think of it as like the original time or the true time. 1 second for the person inside here is going to be just 1 second. So that's the real time that they're going to experience. This person is not going to see any change in how time runs. That's going to change though for an observer. So for somebody outside of the spaceship, and again, we're thinking if 1 second passes inside the spaceship. Okay, just so we have a little bit of a better reference there. Now, what happens is the observed time, so just time in general, is equal to the relativistic factor, sometimes called gamma factor or Lorentz factor, multiplied by the proper time. Or you can think of it as original time if you want to. It's a little bit unfortunate that, observed and original both start with O and the 0 kind of looks like an O. But this is the proper time. The real time that's passed inside the ship is 1 second. Then that's going to get scaled based off of this gamma factor. Okay. Now, unfortunately, gamma, because it's a complex concept, is a complex formula. So we have a big fraction, we've got a big square root under the fraction, and then we have the difference between 1 and then the velocity divided by the speed of light squared. Let me fix my handwriting there, though. Okay, so when things go really, really close to the speed of light, then often we start to use that as a portion of the speed of light or a decimal of the speed of light. So 0.15 times the speed of light. It's not useful so much to know exactly what that is in miles per hour or meters per second or kilometers per hour or anything. So typically what we would do is just say, okay, well, it's a portion of the speed of light, and then we show it that way. And that's useful in this formula. It's slightly refactored to make it useful because if I'm looking for v over c and my velocity is 0.15 c and I divide that then by c, then I get basically just this ratio of how close it is to the speed of light. Excuse me. All right, so I'm only plugging in one number. It just goes in a difficult place to manage because of this formula. So I've got 1 minus 0.15 and then squared. And then we want to work this down and see what it's going to do. Now, we can sort of combine these formulas a little bit, especially because we're looking at T0 as being 1 second. So gamma has 1 over this stuff, and then technically T0 we can say is T0 over 1. And so multiplying these together, we can sort of combine, and we end up with 1 second divided by the square root of 1 minus 0.15 squared. Okay, so we want to sort of start working this down to see what it's going to turn into. And basically what's going to happen is we're going to have 1 second on top all the way through, and then eventually we're going to divide it by some number that's going to scale it. Using order of operations and paying careful attention on what we should do next, we have the 0.15 that we want to square. So 0.15 times 0.15 gives you 0.0225. Then now finding this difference, you want to keep in mind that this is still all under a big square root. This is now 0.9775. And the top still 1 second. So we're not there yet. Like I said, this is sort of complicated. But we're getting close. Let's see. We can do this a little bit more streamlined. So 1 second divided by, if I go ahead and take the square root here, I get something like 0.988, 686, so on, so on. And then now, finally, I can take 1 second and divide by that, and that'll show me how this scales. And so I will get something like 1.01144, and again, that's going to go on and on forever. So lapse time, technically these should all be seconds. There should have been a mention there. But what we're really looking for in the end, like I said, is this scaling factor. Okay, finally, question 3 asks us that directly. So there are a couple of different ways that we can work this through. If you wanted to, then you could manually run through and do that formula again to solve for gamma. But the nice thing is that if we use our formula that we had on the previous question and we notice that these numbers are connected to each other, so if you know the time and you know the proper time, then you can work out gamma directly. So t equals gamma times t0. Remember, observed time and proper time. So because I know those two things, because we've already seen this number, then I can use that as a little bit of a shortcut. Otherwise, we're just running through and finding gamma manually like we did in the last question. Okay, but I can find gamma by rearranging the formula just slightly. So if I want that symbol by itself, then I'm going to divide by T0. And so gamma is T divided by T0. Well, from our previous questions, the proper time was 1 second. The elapsed time, we had 1.01144 seconds. And then you can see seconds and seconds cancel, and that gives us the 1.011. Okay, or like I said, you can manually set up. We've seen this already, but I'm going to give a small reminder. You can calculate gamma directly if you don't have this information like you normally wouldn't. So, it's good practice anyway. But you'd have 1 over the big square root of 1 minus v over c squared, which for this example will be 1 over big square root 1 minus 0.15 squared, which I'm not going to show here because we already did on the previous question. Again, you can back up and check on that. But these are your two main methods for going back and finding that relativistic factor. Okay, then what the next one does, it's a little bit tricky, is we want to work backwards and see what speed is going to make a relativistic factor of a particular number. So you have some options here. Gamma is 1 divided by big square root 1 minus v over c squared. Okay. This one can be a little bit tricky running through and seeing the algebra, or plugging in the formula and solving back around, just because a little bit of an ugly situation with squares and square roots and fractions. So if you're not fully comfortable going through and resolving or using that different formula, then your main option would be to grab answer choices and plug them in and see what's going to happen. Now, with this one, actually, we get lucky because it's impossible for something to go faster than the speed of light. So actually, all of these things are impossible. So we get lucky here that it's the only speed that's under the speed of light. That's the only thing that's even remotely possible. But, normally you wouldn't have quite such easy answer choices. You could plug in a couple of them, maybe eliminate a couple, and then narrow down to see what you need. If you try to solve this through, I'm going to try to give sort of the highlights because you don't necessarily need the algebra and the solving. You just need the formula it turns into. And I will show you that in a minute. Okay. But what happens though is that if we were to solve this, if we were to go through all the steps of trying to get this rearranged and finding the v there, okay, well, we have one side that looks like a fraction and the other side that doesn't. So if we stick this over 1, so I know it's staggered a little bit, but then we could cross multiply and see what that's going to do. Or we have this weird rule of proportions that says we can swap our diagonal terms. So the gamma that's on the top left and this big square root that's on the bottom right can be switched. And so if we do that, we get that the square root of 1 minus v over c squared is equal to 1 over gamma. Okay, then what's going to happen is we'd have to use square to get rid of the square root, and then we'd end up having to move some stuff around a little bit. So, like I said, I'm not going to show all of the algebra here because most students aren't interested in that. Um, but eventually, we're going to work it down. Like I said, we square this, we're going to have to subtract and change some signs. Eventually, we have to take a square root to bring this back down. And so we get to v over c is equal to the square root of 1 minus 1 over gamma squared. Okay, and then because a lot of times the velocities are in terms of c, like these are here, then our final step would be to get rid of the c on the bottom of this. Technically means you multiply both sides by a c. And then our formula, like I said, if you're not interested in the algebra, you can just start here, is going to be that v is equal to the speed of light multiplied by big square root of 1 minus 1 over gamma squared. So if you don't like the brute force algebra approach, start where the stars are. And that's really the only formula you need for this one. C is just a constant, so notice that it just shows up in all of our answers. It's the speed of light. So really we're just trying to solve for whatever's on the bottom. Gamma is this number that's given to us, so we can work that through hopefully without too much trouble. So let's give it a try. We've got the speed of light multiplied by the big square root of 1 minus 1 over, in this case, 1.245 squared. Okay, so this part I am going to show because this is the direct approach and how we finish the question. The c that's on the outside of the square root is basically just going to wait there until we have a number that we're going to multiply with it. So we're going to have 1 minus 1 over 1.245 times 1.245 is apparently 1.550025. Then we want to continue to work this down. So 1 divided by that number is going to give us 0.645150088 and so on. Okay, and then we want to find that difference so that we can finish the square root and see what's happening. So still have c just waiting out here, trying to see what it's going to be multiplied by. This difference now, 0.35484911, and again, so on, so on. And then finally, we want to take the square root of that. Okay, so we'll have c multiplied by, if we take the square root, 0.59569 213. So it just keeps going. But that is enough for us to see, okay, 5956, 5957. Well, that makes sense, right? Because after the 6 is a 9, and that's enough to tell us to round up. So velocity, we're looking at 0.5957 times the speed of light. Okay, so thankfully, we're not going to have all of this brute force algebra all the time. There's just a couple of these that are ugly like this. So, at least we got through it early. Okay, then we're going to go way, way back to something that we saw probably in Module 2. But talking about kinetic energy, we have a formula from that. It comes from calculus. We don't have to see the calculus, but we notice the format. 1/2 something something squared. In this case, 1/2 mv squared. Okay, then it's not quite perfect, but we're going to estimate that the speed of light is 3 times 10 to the 8 meters per second. It's actually very slightly less than that. But if c is 3 times 10 to the 8, then 0.316c is going to be 0.316 times that number. So that's going to end up giving us our velocity here. Our mass, we need to be careful, is in grams right now. So we want to keep in mind that it takes 1,000 grams to make a kilogram, right? So kilo or K means 1,000. So the mass we're using here is 0.062 kilograms. So this question is going to show you that something that's very light here still takes an absolutely enormous amount of energy to get it moving anywhere near the speed of light. So from this, though, we have enough information to go ahead and plug in. We are looking for that kinetic energy. 1/2, we can say, is 0.5. For most cases, that's easier probably to type in your calculator. Then 0.062 kilograms, and then the velocity, we didn't quite work out yet, but it's going to be in 0.316 multiplied by the speed of light, which is 3 times 10 to the 8 meters per second. Then don't forget that in this formula specifically that this last part gets squared. Okay, so let's simplify down a little bit to make sure that we can hopefully avoid some mistakes. So front part's easy enough to do. 0.5 multiplied by that, it's going to give us 0.031. Then multiplying these things together, so keep in mind that we still haven't done the exponent here, but multiplying these two things together is going to give us 9.48 times 10 to the 7. So because that was less than 1, it brought this down, and exponent goes from 8 to 7. Now, we want to look at these units and see what's going on, though. We've got kilograms times meters per second, but this whole thing gets squared, so it ends up being times meters squared over second squared. And as it turns out, that's the same. We can resplit this and say that it's newtons times meters, or we can say that it's joules. Several definitions are similar to each other here. So we don't know what number this is going to make yet, but we have confirmed at this point that these are joules. It's good news because that's what the answer choices indicate. Okay, so then now we want to multiply these together. Depending on your calculator, it may be safer to multiply the scientific notation with itself, or to square it first, then multiply by the 0.031 afterwards. That's really going to depend on what kind of calculator or device you're using. If you can make this work out properly, then you should end up with 2.78598, so on and so on, times 10 to the 14. And then from that, we can pick an answer choice. So keep in mind that the scientific notation that shows up here is generated in Excel with the way that the batches of questions are made. So E, like this, capital E, means that times 10 part. So just to be very clear here, that's the same thing as E, and then because it's a positive exponent, plus 14. Okay, then let's look through a couple of conceptual things on a related topic. So we are going to look at that complicated formula again, but we're not going to plug in and find full solutions. We're just going to sort of plug in and eyeball what we think is going to happen. So here it says, how come we cannot calculate relativistic factors for speeds above the speed of light? So let's say that, just to make things simple, that we picked twice the speed of light, and we wanted to see what the relativistic factor would be for that. Thinking back to our formula, we've got gamma is equal to 1 over big square root of 1 minus v over c squared. Okay, well, 2c means that v over c is going to be 2c over c, or just 2, which makes sense because, again, we said twice the speed of light when we were setting up this example. Okay, well, if we try to calculate that in this formula, we're going to have 1 over big square root of 1 minus, and then 2 squared. Okay, now I hope you see the issue here, because under this square root, if I'm trying to do 1 minus 2 squared, I've got 1 minus 4. In fact, we can go ahead and just explicitly state that that's going to turn to a negative 3, and that means that we're going to have a imaginary, right? Because we can't square root negative numbers normally. And so, yeah, that doesn't really make sense. We physically can't do that. Okay, so what about if it's exactly the speed of light? So let's say we're going exactly c. Then that means v over c is technically c over c, which is 1. Well, our formula, same as before, we've seen it several times. and then we want to plug in a 1 inside of this spot here. Okay, well, maybe you can already see it, but we're in it with 1 minus 1 squared, where, 1 squared is obviously still 1. It's not really doing anything in this case. And that's going to tell us that gamma is equal to 1 divided by square root of 0. On its own, technically, square root of 0 is not a problem, but dividing by 0 is. So we give infinity as an answer, even if we tried to try to come up with something, it would be impossible or too big to measure. Okay, then the question is, what happens if we get very, very close to the speed of light, but we're still less than the speed of light? So we can start with something like, oh, I don't know, 90% of the speed of light. So let's say we start with 0.9 c. Now, because I'm going to show you a few different values, I'm not going to work this all the way out. You can confirm it if you want to. You can also probably find a calculator online that would help you confirm these. But if I plug in 0.9, so 90% of the speed of light, then I end up with a gamma factor that is basically 2.29. Okay, and then let's skip a few. Let's say that I've got 0.9999. So, now obviously getting really, really close to 1c to the speed of light. Then that causes gamma for 4 nines to become 70.71. And then, the more nines we get from there, obviously it's bigger and bigger, right? 3 more nines added quite a bit of size to this. So if I were to go, say, I don't know, 10 nines. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then now gamma, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's this one. 70,000. 710.68. And so the closer and closer we get to the speed of light, the more this number grows. I believe the last one I calculated, I used Excel for this. It's 15 or 16 nines. They're hard to count because they're very small. Has a gamma factor of about 67 million, right? So the closer you get to 1, the bigger and bigger the answer gets. And so it'll become really, really huge if you get really close to the speed of light. Okay, last one. What happens to the values for relativistic factors if velocities get very close to 0? So technically, if we're using 0c, so something is not moving, then v over c is equal to 0c over c, or c cancels, or you can say that it's 0. It doesn't really matter from there. We're just looking at 0. Okay, so gamma, as before, big square root 1 minus v over c squared. We're going to have 1 over square root of 1 minus 0 squared, right? 0, I mean, I guess I'll show the work. 0 squared is 0. 1 minus 0 is still 1, so be careful not to just say it's 0. But 1 minus 0 is 1. Technically, we've got the square root of 1. But yeah, that's 1. And so the whole answer is 1. So if something's not moving, it's not relativistic at all. And so there's no change or dilation or adjustment that needs to be made. So it just becomes 1. Okay, so finally, now that we're like halfway through the group of questions we're going to work on, we're going to move on to a new topic. So the photoelectric effect is what Einstein actually ended up winning his Nobel Prize for, because they could build a setup and understand it better. Also helped to show the difference between the light and wave natures of photons. But what we want to know from this, there's a couple of key pieces of information that tie into how this setup works. So if you have a really big negative voltage, this is going to work against electrons. And so this being a relatively large negative voltage for, the setups and the different things that we've looked at, this is going to stop most electrons. I spelled that entirely wrong, didn't I? Electrons. There we go. So then that means that we're going to need more energetic electrons being kicked off of the metal sample to have any kind of chance at all to produce current. So what we need to understand from that then, and then again, this is part of what Einstein was working on, is that we need to understand that lower wavelengths make more energetic electrons. Okay, so that's part of the relationship between wavelength and frequency. If wavelength goes lower, then frequency goes higher, and frequency is more directly related to energy. At least it's easier to see how they're related. So we want a lower wavelength. That's the big thing here in order to have a better chance of producing current. So this is strictly false. And that was like the main point of one of the things they learned from the setup. And then larger wavelengths are going to have smaller frequencies, which are going to be less energetic. And so here, this is in the range of ultraviolet, so this would not be visible to people, and it's too high energy for our eyes to detect, but it is the most likely wavelength that would produce current in this type of setup. Okay, then let's talk about this one. So again, we have kind of a similar concept. We have this large negative voltage, so this voltage is going to work against electrons. And then if you notice the other voltage is positive, right? So that's going to work with electrons. So basic idea of, how opposites attract. So positive voltage, you can think it's going to help like draw or push the electrons across the setup. It's not going to help make more electrons. It's just going to help the ones that are produced to move faster. So we're not going to get more electrons unless the wavelength changes. This is just going to help push them through the setup faster, which ends up matching this first choice. Okay, then in the next question, if we can hit a hydrogen atom, so that's what we were looking at before in some of our setups. If we can hit a hydrogen atom with the right energy, then we can cause the electrons to bump around to different energy levels, and then as they drop back down, they will release photons in different wavelengths depending on the energy and what's available. So one of the big things we want to watch for is how these things are hit by electrons. If they're hit slowly, then basically they're going to receive just the amount of energy mentioned at the end. And this is in just general context. So there's no numbers here. This technically doesn't even tell us an element. We're just going to assume that the energies are known values. So we have ground state, basically just what the element or atom will sit at when nothing's happening. That's n equals 1. Then in order to bring that electron up to a higher level to get more energy in the electron so that it can eventually do something with it, we would have to bump up to n equals 2 or n equals 3 or n equals 4. And at higher numbers, these get closer and closer together. So I guess they didn't necessarily need to be smaller, but they are closer and closer energy levels to each other. So let's think about how much energy we're hitting this atom with. We're hitting it with energy that is just under n equals 3. So that means it can't quite get to n equals 3, and it means it certainly can't get to 4 or 5. So the only possible option is, if it doesn't excite at all, I guess it could stay at ground level, but the only possible thing that it could jump up to would just be n equals 2. So that seems to be this one. If we'd hit it with just over n equals 3, or if we would hit it with multiple electrons at the same time, we would have seen a different outcome. But notice here that we just couldn't quite get to n equals 3. Okay, so this one, a little bit of a trap here, because you might immediately say, oh, hey, just under n equals 2. So let's sort of draw out our diagram again. You've got ground state. Remember, that's n equals 1. Then you've got n equals 2. Then you've got n equals 3 and 4 and so on. Okay, and then again, you might think, all right, well, it's being hit just under n equals 2, so you might think that it's just going to stay here. But here's the thing. If it's bombarded by electrons, then that means it's being hit with a whole bunch of them at the same time. So you're not seeing just this energy. You could see multiple times this energy. You might get hit by 2 electrons at the same time. And so your energy that would go from here to here is going to bring you up a similar amount. And then now maybe you can hit at n equals 4. Or maybe you're hitting with 3 electrons at the same time. Or 4 electrons at the same time. And again, you could end up accessing every different level. So the biggest point here is that if we're bombarded with electrons, basically bombarded with energy, then those can combine and work together, and they could jump up to a state, then jump up to a higher state, and eventually reach anything. So that one word there is our biggest clue as to what's ultimately going to happen. Okay, so then we didn't have a simulation to talk about for this. It's just something that was in conversation and discussed in the book. But if we involve inner shell electrons, so if we have a larger metal sample or atom that we're bombarding or hitting with energy in some way, then we end up with the ones that are in range for what this is talking about. We have a Z number, or number of protons, that is somewhere between usually 30 and 80. It can be a little bit outside the range, but these are the most common sources for when I tried to look up to find a little more information. And because of the way that the formula works, it's something that we'll study a little bit later. But we've got that z squared in our formula. So think about this then. If you've got a z squared in your formula, and then you're plugging in numbers like 30, 40, 50, 60, 70, 80, then this is going to be thousands of times more energetic. It's going to have a lot more energy to release. It's going to make much more than visible light, but it's just a whole lot more energy. And so that ends up being definitely not infrared, because that's going to be less energy. It's definitely not visible because it's beyond that. Ultraviolet might be your first guess, but the fact that it's thousands of times more energetic means that this is going to be probably producing X-rays. So X-ray machines will use in the range of kilo electrovolts, or keV. And so, that's from sources similar to this. Okay. And then now for our last little group of information, we want to see what happens when hydrogen 3 turns into helium 3. So there's a certain decay process, which is one of these. Be careful, because one of these is a more general term, so we want the specific name, so it's not just going to be beta decay. So that might be a clue, at least to narrow it down. But hydrogen, symbol H, has 1 proton, so that goes in the bottom left-hand corner. If it's hydrogen 3, then that's the number of nucleons, so nucleons, and that goes in the top left corner. And then it's not always given, but your textbook does show it in several places, so I'm going to mirror that. The number of neutrons goes in the bottom right-hand corner. So a lot of times that's not shown, but that's the number of neutrons. I mean, I guess I could label all of these now. I've labeled them, talked about them different places, but might as well formally write it all down. Okay, so then let's see what happens if it transitions or somehow does a thing and turns into helium-3. All right, well, first, helium is the symbol He. Then helium, because of its position on the periodic table, has 2 protons. Then the 3 in the name is the number of nucleons, so that's just here for free. So notice that that didn't change between these. And then if we work backwards to find out how many neutrons there are 3 nucleons total. 2 of them are protons, so there's only one more that can be a neutron. So notice we have the same count on nucleons, which should make sense because there's a 3 on both of these. But look at how your count at the bottom changed, right? So we went from 1 proton to 2 protons, and from 2 neutrons to 1 neutron. So basically, a neutron transitioned into a proton. It was only 1. So let's do it this way. Okay, and so we can draw out a little bit of a better diagram here. So this is a little bit more complex than most of our questions, trying to reason through and see what's happening. But we had hydrogen 3 to start. We emitted some kind of particle, so we've narrowed down and figured out that it's beta decay because beta decay doesn't change the nucleons. So we use a symbol for beta. It has a 0 up top. And then we turn into helium-3, which again, we worked out the notation for what that's going to look like up above. What we need to figure out then is what type of beta item is this, right? So it's not specifically a particle. Technically, it's a couple of particles and a release of energy. But we can use this in our notation to figure out how these things are transitioning. Okay, so we want to see what happened to the numbers, right? So you can sort of set up a subtraction problem, or you can see how things would add and what they would turn into. There's a couple of different ways to do it. I'm going to think about it this way, just as like a missing number type of question, because well, that seems like what we're looking at. This is 1 plus something is supposed to give me 2, right? So look at it, kind of read it backwards. 1 plus something gives me 2. So that tells me that there needs to be a 1 right here. Right? Does that make sense? 1 plus 1 is 2, and so that, shows how this became different pieces, or if we were to able to run it backwards, how it goes the other way. Then the one that's a little bit trickier is, this is 2. 2 plus something gives me 1. Well, how do you add something and get smaller? Think about it, right? You're adding something, the number gets smaller, it has to be a different type of number. It's got to be a negative number. And so the negative 1 right here on this beta symbol is our clue and the part of the naming that it's beta minus decay. Sometimes also called beta negative decay depending on the source, but I believe this book says beta minus decay. But there we go, it's beta minus decay. Now technically, you could have just looked this up somewhere on the internet, I'm sure, but now we have a little bit of a better understanding where all that comes from. Okay, then there are a variety of questions in different places in our material that have this basic format. So we want to sort of make a table and we want to understand what's happening. So a half-life is basically the statistical average amount of time that it takes for half of a sample to go through whatever radioactive decay process it goes through. So say we had, like in the last question, say we had a bunch of hydrogen-3. The half-life for that is how much time it normally takes for about half of that stuff to break down. Now, it's a statistical thing, it's an average, so it's not perfect, but just it's what we expect should happen. So let's think about this. If we have 0 half-lives, then how many particles have not decayed? Well, there's 100 that have not decayed because we started with just 100 and nothing's happened yet. And then how many of these have decayed? If we're at 0 half-lives if no time has passed, then we still have all of them. Then keep in mind what the definition of a half-life means. If we have one, and let me, I guess, label this better, 1 half-life. Okay, so remember, after 1 half-life, whatever period of time that is, we expect half of the material has decayed. So we started with 100 particles that we expect to get cut in half. So, okay, what's the difference, right? From 100 down to 50, that means that 50 things would have decayed. Now, here's sort of the conceptual trap with this one. So a lot of times students think, okay, well, the other half-life is passed now, the other half of the material is gone. but it's always half of the material from whatever the previous step was. So if we have 50 particles here and half of those decay, then we've got 25 left, right? And so we started with 100, we're now down to 25. And so that means that we have 75 particles that have decayed. Okay, and then let's say we go for 3 half-lives. Again, it's not the other half, it's just half of whatever the previous step was. So here, where there are 25 particles, half of those are going to decay, which, you can't really have 12 and a half. We'd have, 12 or 13 or some number close to that, but just for brute force math and writing a table, we want to see how this is going to go. Okay, so now that 12 and a half more particles have broken down, they're going to go into this other category, or you can take this number, subtract that number to do it directly, but this will give us 87.5. Okay, so then let's read the question and see what's going on here. Because sometimes it'll ask you for different numbers of half-lives, and then also it'll say decayed or not decayed. So here, 3 half-lives, which means I'm looking at this point, and then the ones that have not decayed means that I want to grab the number from here. Again, these are all around because it's a statistical thing. It's average or an expectation, and then also you can't have a half a particle broke down. Either it breaks down or it doesn't. But here, around 12 is our closest answer choice. Okay, then our last little run of practice questions where we're going to look at some of the different forms of decay. So some of these are energetically unfavorable, basically unlikely to happen. But I picked uranium-238 just as a random example because uranium has many, many different isotopes and many different ways that it can break down. So we're just going to assume that the process is able to happen and then calculate what it would become if it could happen. Okay, so forgive me if some of these things are not technically physically possible or if they're very unlikely. It's more about learning the process and seeing what's going to happen. Okay, so uranium has an atomic symbol of just U. This is uranium-238, so remember that goes in the top left corner. Then you would need to probably look up uranium to see how many protons it has, what the atomic number or Z number is. That's 92. So if it doesn't have 92 protons, it's not uranium, it's something else. Then for our convenient notation, the difference between these numbers will give us the number of neutrons it's at the bottom right. So subtracting those will give us 146, and that's our base or parent nucleus. So this is the thing that's going to decay in some way and turn into something new. Okay, so alpha decay, we haven't talked about in this group of material yet, but alpha decay means that we're going to go through and release an alpha particle. So an alpha particle ends up just being a helium-4 nucleus. So helium, I guess I'll spell this one out, helium-4. Technically, we've talked about helium-3 already, so we know kind of the information, most of it, or at least the process for how to find it. So helium, atomic symbol He. All helium has 2 protons. This one in particular is helium-4, so it has 4 nucleons. Okay, and then to fill out our convenient spot to know how many neutrons are here, 4 minus 2 is 2. Okay, then we don't know what this is going to make. So for right now, let's just say this is element X. Okay, then we want to work through these pieces, see what it's going to have, and then go from there. One of the biggest things that we need to pay attention to is that the number of protons specifically is changing, so this will be a new element. Okay, so let's look. Across the top, we had 238 total nucleons. 4 of them are ejected with the alpha particle. So whatever this thing is, it has 234 nucleons left, which I guess technically gives our answer away, but let's work it through and see if we can confirm the rest of that. Okay, so now if we look at the number of protons, we had 92 protons. We ejected 2 of them with the helium nucleus. We now have 90 protons, which is an element that we will look up in a minute. Then for our neutrons, we had 146 with this uranium isotope. We have 2 that are ejected with the helium, so that means that we're going to have 144 here. Okay, then if we look it up based off of the Z number, off the number of protons, then yes, this is thorium, which is Th. Technically, it's thorium-234. So if we recollect all of this information and write our full symbol, then it looks something like this. Okay, then let's find out what's happening with the next one. So uranium-238, I used the same symbol in these original examples just so we can consistently see the difference there. But this is U, then the same numbers around, so 238 because of the isotope, 92 because it's uranium, and that's always true, and then 146 is the difference in those. Okay, so this time it's going to go through beta plus decay. So we talked about a beta minus particle, and again, it's not truly a particle, it's a couple of things, but it gives us a notation to find out what does it turn into. So we're looking for this thing at the end. Okay, so beta never changes the number of nucleons. What happens is a proton will transition into a neutron, or a neutron will transition into a proton, one or the other, and then we'll get different elements from that. But they will have the same number at the end. So technically, we know that it's going to be one of these and not the first one. Okay, but then let's look through. Beta plus means that this is going to be a +1. And then to balance our charges for conservation, then here we're going to have a -1. So +1 and -1 makes 0. The beta plus decay part, again, plus, is indicating the sign that's in front. Okay, then let's see what this is going to turn into. So for now, we're just going to say it's element X, and we'll work that through in a minute. Because of beta decay and the fact that there's always a 0 at the top in the notation, this is still going to be 238. But then let's look and see, right? We have 92 minus 1 is going to give us 91, right? So what happens is it looks like we lost a proton, but let's see what's happening with the neutrons. We have 146, technically subtract -1, right? So subtracting a negative is never really subtracting. It looks more like addition most of the time. But we get 147 here. So notice that something came out of this column basically and went into that column. So a proton turned into a neutron. Then now we have a different number of protons, or Z number has changed. So if we look up the atomic number 91 in our elements, then that is protactinium, Pa. And then let's finish out our notation. So we've got Pa, we've got 238 here because again, beta decay doesn't change that number. Then 91, which is what led us to say protactinium in the first place, and then 147 drug down from our previous information. So looks like this one. Okay, very similar question, but this time beta minus decay. So we saw an example of beta minus decay earlier with hydrogen 3 turning into helium 3. Let's see what it is for uranium now. All right, so uranium 238 from the example. If we look that up, or you might remember by now, uranium has 92 protons, then the difference in these two numbers is 146. Okay, then beta minus decay means that our beta notation here, we've got 0, this is going to be a -1 in front, then to keep balance, we'd have a +1 on the other side. Plus whatever element X, we don't know what this is going to turn into yet. So minus here means minus here. Then let's work it out, right? So 238 minus 0 is 238. 92 minus -1 is 93. And then 146 minus 1 is 145. So if we look this up, then based off of the number of protons, 93 protons is going to make this Neptunium, so NP. Then 238 preserved from the beta decay, 93 from the protons, and 145 from the notation. All right, then one last question. Gamma decay. So gamma decay, I'm really going to kind of abuse the notation a little bit here. It's not normally shown like this, but just to be consistent to show what's happening. If there's a little asterisk or a star here, then that means it's an energized form or an excited state of uranium. So we've got uranium, it's 238. Technically, all of this is stuff we've seen before. Although my pen's acting up, let me fix my handwriting there. Then The energetic part, the star that's here, just means that it has more energy. And so what will happen in gamma decay, there is no particle change. So like I said, it's really an abusive notation. You don't normally see it this way, but if we really wanted to stress the formula, technically we'd have all zeros. There are no real particles moving with this. Gamma ray is just pure release of energy. Electromagnetic wave carries energy, no particles or real pieces to it. So technically what we get from that is still uranium, and exactly the same kind of uranium, but now just with the less energy. So notice that the little star is gone. So it goes from an excited state, drops back down to just regular uranium. Not only is there no change in protons, there's no change in nucleons, neutrons, nothing. It's exactly the same thing, just now with less energy. All right, and that's it.